Hi everyone and welcome to this lecture. Today we are going to discuss about the Cauchy principal value and something called an indented paths, and this will be helpful. That is the theory that is discussed here in our future videos to evaluate some exotic kind of counter integrals that involves improper integrals as well. So let us start our discussion with the evaluation of a simple integral like this. Limits a to b f of x dx, and let's say x0 is a point that lies between a and b, that is denoted like this mathematically, and on this point the function itself is singular. So at this point f of x is singular. What do I mean by that? I mean that if you take a limit x goes to x0 of f of x, this is something like this. It's either infinity or it doesn't exist. Or let's say it's diverges. So if that is the case, what do you do? What you can do is that you can write this integral, let's call it I, and you can break up I like this. This breakdown is familiar to you from your 120 improper integral course, and if you have such a singular point that lies between the interval you are integrating, you need to evaluate this thing and you need to check the limits. If they exist, then the integral over here, it will exist, and if it doesn't exist, the integral won't exist. That means this limits. So the very idea of Cauchy principal value comes from the fact that if you take this delta and replace it with epsilon, that is, this delta is going to epsilon, then your I, the integral, now becomes something like this. Goes to 0 plus a to x minus epsilon f of x dx plus limit of epsilon goes to 0 plus, and you have your b x plus epsilon, and you can get rid of the plus and you can also write it as epsilon goes to 0, and this is the resultant thing, and this is known as the principal value, in short written as PV, of the integral that you see over here. It's sometimes also denoted with like this, an integration, and there is this cut thing, and then there is this f of x dx. So I defined this principal value like this, and what does the principal value mean? Well, at point x0 the function might diverge, it might not exist, it might have some singularity that is occurring. However, you can still make sense of the integral using this principal value thing. That's why it's important. So if you consider some simple examples, you can prove that this integral that ranges from 0 to 2 of some function x minus 1 by 1/3, this integral is convergent, meaning that even though at x equals to 1 the function f of x is equals to 1 by x minus 1/3, this at x equals to 1 it doesn't exist, right? However, you can see that 1 is lying between 0 and 2, but still if you consider this type of breakdown that is given over here, and if you try to calculate this integral, it will evaluate it to be some finite number. That's why we're calling it convergent. And there is another kind of integral. If you consider another example like this, dx by x minus 1 whole square, you'll see that this is divergent. Why? Because we see the principal value doesn't exist, and in this case the principal value exists. And this is coming from where? This is coming from this equation over here, this guy. So how will this help us in evaluating contour integrals? Well, so far we have only discussed functions that had singularities in the complex plane, and we only consider such singularities that are not relying on the real number line. But here you can see that this function over here, that at x equals to 1, this point 1 that has a 0 imaginary component, that means the imaginary component being 0, this 1 is relying on the real number line. Okay, same goes here. And that's why what one wants to do is that one wants to avoid the singularities, or so to say, avoid this kind of poles. So if I draw a geometric picture, let's say you are considering an integral that ranges from minus infinity to infinity, and you have this e to the power ix by x dx. This is the thing you are considering. So you might think that, okay, there is some singularity at x equals to 0. This is a pole. That means it's a singular point. So what you can do, you can draw this complex plane again, and if you try to draw your path, let's say I denote it with the green line. It starts from minus r. You go from here, here, here. However, there is this 0 thing, right? So this is where you want to avoid the pole. You are moving on to the real line, but there is a pole and you don't want to hit the pole, because at the pole the function itself is not defined. So that's why you go around it like this, a small semicircle, very small semicircle, and then you move on to r, and then you close the contour. So if you call this contour as C capital R and call this contour C epsilon, this means that if you enlarge this area, this will look something like this, where this is the singular point. That means z equals to 0, or let's say x equals to 0, whatever you want, and the semicircle is like this. The epsilon is the radius of this smaller semicircle. So this is the geometric picture of the principal value thing. So whenever you are considering an integral like this, you are actually calculating the principal value. However, most of the time it is not mentioned, but it's a good thing to know that it's called the principal value. And since we are considering another circle like this, we will need some other theorem, let's just say one extra theorem, to evaluate what happens in this smaller circle. And in the beginning I told you that I'm going to discuss these indented paths. So the picture you see here and the smaller circle you see, this is known as the indented paths. That means if you ever have a pole on the real number line, you just go around it. That's an indentation. So what if you had, let's say, more than a pole? Let's say you had two poles like this, one over here, another one over here. So you would just go around this like this. Okay, and this is only valid when the integral is from minus infinity to infinity. And now I want to discuss another theorem. and this theorem will be helpful for us in evaluating integrals like this. So the theorem that I'm going to discuss right now, let's try to do it from the geometric point of view. So again, we will consider a contour like this, and we'll mainly focus on this part, that is the smallest circle with radius epsilon. So let's say, okay, this is another theorem, so I should write a theorem, and again we won't present any proof. We'll take it without a proof because the proof is a bit more mathematical. So let's say f of z has a simple pole at z is equals to 0, z0, like this. And let's say this is your z0 point. And when you are approaching it from somewhere, let's say like this, an arbitrary path, you are going around it. Okay, the picture doesn't look very good, so I need to draw it again. Sorry for that. So let's say this is your z0, and you are approaching like this, and you saw the pole and you want to go around it like this, and then you go like this, and then you close your contour like this. And let's say it makes some angle. That means this point, this line that should have ended like here, and this line over here, it makes some angle. This angle is called phi. Okay, so for this f of z, it has a simple pole at z is equals to 0, and this is the path that you are choosing to go around this pole and close your contour. Or let's say you don't want to close it, that's up to you, but we're going to consider that we're going to close it like this. And this guy over here is known as c epsilon, that is a circular arc with this angle phi. Now the theorem that I'm going to discuss is actually has actually two parts, and let's say the first part says, suppose on the contour c epsilon that we depicted in the figure over here, we have, so let's say this is part A, and it says that on the contour c epsilon, let's say along this contour we have z minus z naught times f of z goes to 0 uniformly, that means smoothly, as epsilon goes to 0, that means the limit epsilon tends to 0, then the integral that is defined on the smallest contour, that this guy c, it will be taken with the limit epsilon goes to 0, and this will be 0 as well. So it tells you that what happens when you go around this pole. Do you pick up something or do you don't pick up something? That means whether you pick up a residue or not. So you have to check whether z minus z naught times f of z, whether this goes to 0 or not. If that's the case, when epsilon goes to 0 uniformly, then this limit is 0. This is one part of the theorem. And the other part is that, this is one case of the theorem that I'm discussing right now. And this says that suppose f of z has a simple pole at z is equals to z naught. However, you can find a residue. That means this condition over here, if this doesn't apply to the problem you are dealing with, you have to refer back to this B. So this says that if f of z has a simple pole at z naught, pole z naught, then if the residue of f of z naught, that means at the z naught point, or let's say, okay, let's not write it like this, let's write it like just z naught, because you understand from the context that we are calculating a residue for the point z naught for this function. And let's say this residue is just C minus 1, like this. Then for the contour, C epsilon, again let me remind you what is this C epsilon is. That is this guy over here, that is this smaller path. And for this contour, when you take the limit epsilon goes to 0, you will have C epsilon, that is just indicating that integral is defined on that contour. C epsilon f of z dz will be I phi C minus 1. This is the residue, this is the angle that it makes. That means you go from here to here. Let's say this is point A, this is point B, and from going to point this point A to B, you make some angle phi that is denoted over here. This is that phi angle that you are seeing over here. So these two results are important and you need to keep them in your head when you evaluate these indented path things. That is, first you need to check whether this rule applies. That means you have some function, let's say for this function, right? Let me just give you an example with this function. And yes, before I show this example, you can see that though my diagram, on the diagram I'm going clockwise, this theorem is actually proven for the anti-clockwise thing. That means you are going around this C epsilon on the anti-clockwise direction. So let me just write anti-clockwise direction for this guy. If you just go to the clockwise direction, you will just pick up a minus sign. That's it. That's the difference. And let me now show you an example using this function that, okay, where was that? Using this function. So I'll just show that which theorem will apply. That's it. So this is an example. We are considering this integral e to the power I x dx, right? So first things first, you are going to promote everything to the complex variable, and this is a minus infinity to plus infinity integral. That means our contour will start from, let's say, this minus r, and okay, let me use another color for that, r. This is plus r. This is our singular point, that is the 0 thing. So we are going to start from, let's say, this part will go like this, we'll move around it, we'll go like this, and then we'll close the contour. So this is our CR. This is let's say this is our minus epsilon and this is our plus epsilon, because we are considering this part like this. It has a, this is the 0 point, the point of singularity or the simple pole, and we are considering the radius to be epsilon, right? And now we just want to see which of the theorems, that means whether this part A or part B will work. That's the thing we want to see. So part A only works if you have this singular point z0, and if you multiply z minus z0 with f of z, and that goes to 0 when the limit epsilon goes to 0, right? So let's try to see whether for this function that is true. So here our f of z is e to the power iz divided by z. So f of z is e to the power iz by z, and z0 will be 0 this time. So z minus z0, f of z will be simply z times z e to the power iz, and this is just e to the power iz. And if you take epsilon goes to 0, that means the thing I showed over here, you need to check whether this guy goes to 0 as well. Okay, so now you might be confused because there is no epsilon over here. So how can you tell that? So the way to see this is the following. When you shrink this smaller circle C epsilon over here, that is this, when you shrink it and you take this epsilon goes to 0, notice that you will almost hit the pole. that means something like this. Obviously you will never reach it, but you will almost hit the pole. So the idea of here is that since we are dealing with the function that is defined on these contours, we just take the limit z goes to 0. That means you just take this guy and you are taking the limit z goes to z naught, something like this. Okay, that's one way to see it. So here we need to take the limit z goes to 0 because that is our singularity, and this is just 1. So this is not 0. That means theorem A won't apply, or let's say the part of theorem A won't apply. That means this is not true. So if this is not true, then this must be true. So we have a singular pole, or let's say singularity, or a simple pole, and we'll get some residue out of it. And here in this case, you are when you are moving from minus r to minus epsilon, notice that along this smaller semicircle you are going on an anti-clockwise rotation. And let's say for this function f of z is equals to e to the power I z divided by z, there is some residue c. This is our residue at 0 for this function. So according to theorem B, that is written over here, that limit epsilon goes to 0, that means as the smaller circle shrinks down, you will have this I phi c minus 1. Obviously this is for the anti-clockwise case, but we're going on a clockwise direction, so we'll pick up a minus sign. And here the phi, that means the angle, you can notice that this angle that is going from here to here is simply pi, right? And you are going on a clockwise direction, so you'll have this c epsilon, that is the integral on the smaller circle of this f of z, that was denoted as e to the power I z z dz, as negative I because it's going on the clockwise direction. The phi is pi, phi is replaced with pi, and the residue, whatever the residue is, you need to calculate it, and you will see that this is just minus I pi and this thing, right? So this technique will help us in our next videos, where we will see some integration with this kind of indented paths. And in fact, in the next video we are going to solve this integral in a more formal manner. So this will be it for today, and I'll see you guys on the next lecture. Thank you.